Hello, Science Alliance. My name is Lara. This is State of Science. I am trained to teach physics up to A level, and now I just stream free live lessons into the internet. It's like busking, and I say, can you put some money in my hat if you like it? So I'll ask you to put money in the hat at the end. I won't now because you might not like it. Now, I'm trained to teach physics, so I've taught like IGCSE physics before, but I haven't actually ever taught IGCSE astronomy. So I've learned some things because in IGCSE physics, we learn a lot about light and lenses and how they work. In fact, we're sort of doing two of my IGCSE lessons in one in the first like 6 minutes of this lesson, so we better crack on. I said to bring a blob of blue tack and something waterproof. To be honest, you really don't need the blue tack. You don't need it. I've done this activity twice now on Facebook, and it's better without the blue tack. But it's such a boring activity, I guess, if you don't have one. Just get a bit of waterproof stuff that has got writing on it. What you do is you just put a blob of water on it. That's all you do. And see what you observe. So that's why it has to be waterproof. It's got to be something shiny that you don't love. It can't be like a book or something. Let's just get a tablespoon of water. Well, not even that. A tiny little bit of water. Put it on some small writing on a waterproof thing and see what you see. There we go. Simplified it. Have you decided what you're going to observe? That's important in science, that we don't just do stuff. You've got to think about it. Blob. There we go. There are more activities. I'm going to make you do two more things with that spoon later. Is that what you were expecting? Oh, I think that's very clear. It's magnified, isn't it? It's bigger. It's definitely bigger. So obviously the more interesting question is, why is it bigger? Well, that's what we need to talk about today. So, light travels in straight lines, right? Light travels off things that are emitting light. So like the sun is giving off light. So we see light from the sun when it just comes straight to Earth. I'm going to bang on about this, and I don't care if it slows the lesson down. Do not ever look at the sun with your eyes. It's because your body has evolved so that when you touch really hot things, you immediately pull your hand back. Like that signal doesn't even go to your brain. Your whole body just goes, no, that doesn't happen with your eyes. You don't have like pain receptors in the back of your eyes. So if you look at the sun, you'll be like, I don't know what I was talking about. This is fine. It's because your body isn't sending you the signal. Your eyes are getting horribly, horribly damaged until it's too late. So sorry, that wasn't a very nice way to start the lesson, was it? Never look at the sun. But light is emitted from the sun and comes to Earth, and that's how we see it. The moon isn't giving off light, is it? It's not like a candle, but light is bouncing from the sun off the moon and then to us, and that's how we see it. Stars give off light. They're so far away. We looked at this in our first astronomy module, that by the time that tiny little bit of light has travelled all the way across space and hit Earth, sometimes it just misses. Sometimes it hits the air in Earth and bounces off. So if you're looking at a star and it's sort of twinkling and flickering, when it's not there is when literally the light from the star hasn't got to your eyes. I know. So we need to talk about why this little blob of water magnified our thing, our writing. I'm not used to fudging, but this lesson isn't supposed to be about lenses. It's supposed to be about telescopes. So we are going to fudge a little bit. And move on a bit faster than I normally would do. Light travels in straight lines, but it can bend. Let's just do this activity as well. So if you get your spoon and hold it by the spoony end, if you get a glass of water and you put the spoon in the centre of the glass of water, what do you see? It's magnified, isn't it? It's magnified. So this is one thing that a special kind of lens can do. And you'll have seen it because they have this lens in magnifying glasses. It's a lens that is shaped like this. This type of lens is called a convex lens. I might need you to remember that for a quiz at the end. So convex lenses are usually like bits of glass that are curved. And what they do is, we won't go into the details, but they can act as a magnifying glass. They can make stuff bigger, right? Which hopefully is quite easy for you to remember because that is the shape of a magnifying glass lens. But it's also the shape that your water was, right? So you sort of created a little convex lens out of water when you put some water on your milk carton or whatever it was. And this glass is acting like a magnifying glass as well. Some of you will have a different shaped glass and you'll find that it's actually got smaller, which is fine. We'll sort of talk about that a bit later. Now, I know this is really obvious, but it's also really cool. If you put your glass, your spoon right in the middle of the glass and then you move it to the side, look what happens. Oh, it's so good. Like, I know we live in the world and we've probably seen this sort of thing before, but it's really cool, right? Like, why is that happening? The bottom of the spoon is magnified because it's sort of in the lens, if you like, isn't it? It's in the glass of water, and the top bit isn't. But it also looks like the glass is cutting the spoon in half. What's going on? Okay, the classic way to demonstrate this is to use the idea of a road and some grass. So I want you to imagine, I'm going to explain why you see that. Imagine that I've got a car and it's travelling on a road, and it's very easy for the car to travel along the road. The road is very smooth. And then the car hits some grass and the grass slows the car down. Okay, so if everything was just straight on like this, here's what you would see. Car travelling along, I don't know, it's travelling in the middle of the road. Both wheels hit the grass at the same time. Car goes from fast to slow. And we could do it the other way around, right? Car goes from slow to fast. That's what's happening when you put your pencil or your spoon or whatever right in the middle of your glass of water. It's the rays of light are hitting the glass or coming out of the glass dead on, so they're all speeding up at the same time. If we angle this bit of grass, what happens? If you watch my free live IGCSE physics lessons, then you will know this. Car travelling along. Suddenly the far wheel has hit the grass, so the far wheel has slowed down, but the wheel closest to us is still going fast. So what's this car going to do? If this wheel's going fast and that wheel's going slow, what's it going to do? It's going to do this. It's going to bend, right? It's going to turn. Is that okay? That wheel, if you like, you can imagine this wheel is going so slow that it's still, but that wheel's still kept travelling. So that would happen. And again, if it was happening this way around, it would curve just in a different direction. Now this wheel's fast and that wheel's slow, so it does that. This is what light is doing when it comes from your spoon out of the glass. So it's travelling like this. It's hitting the glass at an angle, so it's bending. But your brain has learned, because of living on planet Earth, that light travels in straight lines. So it's an optical illusion. It's amazing. The spoon carries, the light from the spoon carries information. This is a spoon into your eye. But your eye sees the light coming from this direction. It's like, oh, okay, information about a spoon. It must be over there. It's good, isn't it? So light bending, and I need to throw some physics words at you quite quickly so that we can start learning about telescopes. But it's okay, because I'll just keep repeating them again and again until it's fine. Light bending is called refraction, right? Refraction is light bending. I know it's a posh physics word, and it just means light speeding up or slowing down and bending. So that is refraction in action. So what a convex lens does is, if light is travelling towards the convex lens like this, you can see the convex lens is lots of different angles. So what ends up happening is this bit of light gets bent that way, that bit of light gets bent that way, this bit of light, because it's travelling through the middle of the lens, goes straight ahead, and all the lines cross. Okay, so lots of physics information, but we'll keep coming back to this. This is basically how telescopes work and what the whole lesson is about. Where the lines cross is called the focus, and that is where the image is. That's where you see the image, where the lines cross. I'll put image. Exclamation marks is cool. And what we're going to talk about quite a lot today is the distance between where the image is, where the lines cross, the focus, and the lens. So this bit here, just this distance, is called the focal length. I'll leave this on the board so that we can keep going back to it, because that was a lot of physics words all at once. All right, so we've got a convex lens shaped like this, which makes light refract, bend, and all meet in a point like this, all come together, which is called the focus. But the important thing is that that's where the image is. And the distance between the image and the lens is called the focal length. Your body has got this down, probably, because this is exactly what is happening in your eye. If you've got a typical eye, and obviously we do not all have typical eyes, I'm always fascinated by you lot telling me about the different eyes that we have in the science lines. But a typical eye has got a convex lens. There it is, right? The sort of curvy, outy one. So light travels through your convex lens. The lens bends the light in different directions so that it meets. And if you've got a typical eye, which works well, the image, the focus, where the lines meet, is exactly where the back of your eye is. So that's where the cells detect the image and send the message to your brain. If you don't have an eye that works quite right, like if you need glasses or something, what will be happening is maybe the lens is focusing the light at the wrong point, so it might focus it too early. The image might be there, just floating in the middle of your eye, or the image might be like sort of there past your eye, and then you've got to put a different lens in front of your lens to bend the light differently so that it meets in the right place. I know, right? Yeah, amazing. Okay, phew. Are we finally ready, I think, to actually talk about telescopes? We have all of the words that we need. So the first telescope that was ever invented was the first sort of proper great telescope that everyone talks about is the Galilean telescope. So Galileo, incredibly famous, didn't actually invent the telescope. Heard about the telescope being invented and was like, that's a good idea. I will immediately improve it and build my own. So that's the Galilean telescope. If you do end up doing like IGCSE astronomy, the cool posh exam, you will learn about the Galilean telescope and another one. I've kind of mashed them all together. We're just going to talk about the refracting telescope, because that's what the Galilean telescope does. It refracts light. Light travels through a lens and it bends. I've got it here. I wrote it down. Now, in fact, I'll show you the picture first. Okay, so this is a refracting telescope. Light comes from the moon, travels through a massive big lens in the end of a telescope that bends the light, refracts the light. The convex lens refracts the light. Here is the image here, and then the light obviously carries on, spreads out a bit more, and then you've got a second lens there, and you look through that lens. There you go. Now, I was thinking that would be the telescope that you drew. I said at the very start of this lesson, like, if you want to just sketch a telescope while you're waiting and label the bits. That's like the classic pirate on a pirate ship looking out to sea telescope, isn't it? You've got a big lens there, you've got a little lens here, right? I shouldn't be embarrassed about this, because it was a lovely, interesting learning moment. I've taught lenses a lot. I've never taught telescopes. I looked at that picture and I was like, what? Wait a sec. If you got questions when you look at this, some of you will already know this from studying telescopes. I was like, well, wait. Big lens, bringing the rays to a point. You got the image of the moon there. Why do you need that second lens? Why don't you just do this? And I hope you appreciate how long this took me to do on PowerPoint. Why don't you just do that and put your eye there? That would be better, wouldn't it? You've got a big lens, you've got the image. I mean, lenses, what are lenses? They're just glass, massive bits of glass that have to be perfectly smooth on both sides so that the light focuses correctly. Like, they're expensive. Why would you have two of them when you can only have one? I think I just improved on the refracting telescope, chums. Can you answer that question? I don't think I would have got it if I hadn't looked it up. Why isn't that a telescope? Now, some of you will just know. I'll be very impressed if any of you can work it out. We have talked about it, actually. I mentioned it quite a bit at the start of this lesson, what lenses can do. The answer is, that image is tiny. That's a teeny weeny little image of the moon. So the second lens is a magnifying glass so that you can see that tiny little image of the moon. I don't know why this has absolutely delighted me. It's adorable. You get the light from the moon, you bring all the information about the moon much closer to you, and then you look at it through a magnifying glass. Isn't that awesome and brilliant? So that's what the first telescopes were doing. So good. But anyway, I've written on the board, there are some problems with this kind of telescope. There are, yeah. Well, I'll tell you the big problem. To get a detailed image, you need to collect light from things that are really far away, okay? Just like if you wanted to collect loads of rain, you would have to have a really, really big bucket or loads of little buckets. If you want to see images in great detail, or if you want to collect loads of light from something that's really far away so that you can see it well, you need to collect lots of light. That's what telescopes are. They are things that collect lots of light. So in order to do that, you need a really big aperture. Aperture, basically just a sort of posh word for hole. So if this is a cool old-fashioned telescope, the aperture is the bit that collects the light, yeah? So you need to have a big one of those to collect enough light to get a really good image. Why is having a big aperture on a refracting telescope, a telescope like this that bends light with a lens, why is having a big aperture, a big hole, a problem? It has to do with something that's on the board, and the diagram in the board is only 4 lines, and it has to do with 2 of those lines. You might be saying, because you need a bigger lens. Why is having a bigger lens a problem? Well, there's actually loads of reasons why having a big lens is a problem. There's so many problems. I will attempt to list some of them. First of all, a big bit of glass is really heavy, right? So a big lens would be really big and heavy, and it's got to be like clipped into the telescope only right around the outsides, hasn't it? You can't like put a big thing in the middle to support it, because then you wouldn't be able to see the image. So glass is really heavy, which makes it difficult to actually make the telescope. Like I say, it's got to be perfectly smooth on both sides so that the light is perfectly focused, which obviously is a really big job if you've got a huge piece of glass. Also, I mean, if you get your glass of water and you look through it, you will find light is not travelling very easily through the glass of water. And if you imagine that was a swimming pool, it would be even harder, wouldn't it? Like, the more glass light has to travel through, the more it's going to move around and get distorted, and the less clear your image is going to be. There's another problem, which I found some diagrams about, which pleased me, so you can have a look at these. If you did watch last week's lesson, we made a rainbow. We looked at how white light, when it travels through like light, glass or water or whatever, and it slows down, it can spread out into all the colours of the rainbow, which was nice. It's not very good for astronomers. So here we've got all the colours of the rainbow all mixed together, so it's white light hitting this convex lens, converging, but the blue light is being refracted more and the red light's being refracted less. So this leads to this thing called chromatic aberration. Here is the internet's favourite copyright-free image of chromatic aberration happening. It's great if you want to make it look like horses. I've got like cool shiny purple hair, but it's not very good for astronomers. And the other problem is, it's this thing that we looked at called focal length. So focal length, the longer the focal length is, the better. I did this on Facebook without showing you any diagrams. I just sort of said, the longer the focal length is, the bigger the image. And I really didn't like saying that, because that's I really don't like it when people just tell stuff to kids without explaining it, and you just have to remember it. Like, the longer the focal length, the bigger the image. How can I remember that? I don't understand it. So I've got the diagram for my IGCSE physics. You don't have to understand it, but it might at least sort of help it to shuffle the fact around in your brain. Yeah, I'll show you. It doesn't matter if you don't. It's just, I think it'd be useful for you to see. So this is our convex lens. We did a whole lesson on lenses at IGCSE, so I explained this more. This is an imaginary line going through the lens, and what actually happens is, if you say that this is the object here, light travels from the object and then gets bent by the lens, right? Another ray of light, because light's bouncing off the object in all different directions, so one ray of light goes like that, hits the lens at an angle and travels down there. Another ray of light just comes from the object straight through, and where the lines cross is where the image... Oh no, I've done it wrong. This is what I was working on. Wait, I'll have to... Oh no, I've moved them both. Ah, disastrous. The reason I was late on, if you were watching live, is because I was trying to do this for you, so it would help you understanding, because I hadn't showed them in the lesson on Facebook yesterday, and I thought it was a bit dodgy. There we go. This is totally seamless, isn't it? I would say talk amongst yourselves, but you can't, because this is a YouTube lesson. I think I've fixed it. Let's try that again. Pretend that never happened. Here we go, children. So if you imagine the image is there, the object is there, let's say that's a tree, I don't know, light travels like that, and then it goes like that, and also some light goes like that straight through. Oh, there we go, look, so where the lines meet, which is actually sort of there, isn't it? is where the image is. If this lens made the lines focus a bit later, then what would happen is the lines would end up crossing further away, and you can see sort of on here that that would mean that the image is bigger. The pink arrow is the image. Like I say, you won't understand that because I haven't explained it to you, but hopefully just seeing that is going to slightly help you to remember that the longer the focal length, the longer the distance between where the lines cross and the lens, the bigger the image. You can imagine if this went all the way off the page, then you would have, if you had a really, really long focal length, then the image would be massive. Anyway, it's important that you know that the longer the focal length, the bigger the image, and that's better, right? It's clearer. But in a refracting telescope that we've just looked at, if you want to have a really, really long focal length, you need to have a really, really, really long telescope. It's all getting very impractical. So Isaac Newton solved this problem. There is a thing called a Newtonian telescope, which works differently and is better, generally speaking better. But instead of just showing you what a Newtonian telescope is, because that's boring, isn't it? I was thinking maybe I can get you to invent the Newtonian telescope. Again, just think the same way that Isaac Newton, one of the most famously brilliant scientists of all time, thought. Yeah, simple. So let's see if we can do it. Here we go. So we've got a refracting telescope, convex lens, light travelling, being bent by the lens. But we can't make it very big because the lens is too heavy. We can't really get it smooth on both sides. You need a long focal length to get a really good clear image, but that would make the telescope really long. We need a different way of doing things, okay? We need a different telescope. Can you solve the problem? So let's just go right back to the beginning. What is a telescope actually for? What is the point of a telescope? It is to collect light. So can we think a little bit outside the box here? How else could we collect light? Is there anything else we could use to collect light and make rays of light all focus to a point? That's what we really need to do, isn't it? We need to collect light coming from the moon and make it focus at a point so we can see the image. If you're sitting there like, I don't know, don't worry about it. I'm going to tell you. Just going to make your brains work a little bit first. It's like trying to do a push-up. Even if you can't do a push-up, trying to do a push-up will be working some muscles, even if it looks like you're not moving at all. And that's what's happening with our brains right now. How else could we collect light? We could collect light with a thing that you have almost certainly got in your house right now. Some people have these things in their bags. You could use a mirror, and not just any kind of mirror. Well done, Isaac Newton, here he is. You could use a curved mirror. Okay, look at the screen now, look at the screen, because I'm still not going to give you the answer. I'm going to ask you to build a Newtonian telescope in a sec. But I need you to know how this curvy mirror works, okay? Let's make some light travel from the moon, bouncing off the sun and then onto the moon and then bouncing into our eyes. So if light hits the mirror like this, just dead on like that, this mirror is now, you've got to be looking for this bit. This mirror, the light is going to bounce off the mirror, but because the mirror is curved, the light is going to end up bouncing back off the mirror like this. Oh, it's met at a point, chums, it's met at a point. If we put our eye there, we see an image. Okay, I've said too much. Right, so this was a brilliant solution because mirrors are very different to lenses. You only need to get one side nice and smooth because this side of the mirror isn't doing any work, so that's great. And they're also much, much lighter. If we could get this mirror somehow into a telescope, we would have a good thing on our hands. Okay, so I'm still not going to give the answer. I'm going to show you the ingredients that Isaac Newton had and say, can you make a telescope that collects light and beams it into your eyes? You have the moon, you have a metal tube, you have a curved mirror that behaves the way that I just showed you, you've got a teeny tiny little flat mirror, well, sort of flat, for our purposes of this diagram it's flat, that can reflect light at an angle. And also, extra little clue, there's a hole in the tube there, in the side of the tube. Have a go. I was delighted with this on Facebook because I could really hear people thinking. People were getting some bits right and then sort of going wrong at the end and then trying to solve the problem. I love it. I loved it so much. I'm going to run off and top up my coffee, and you've got the time it takes me to run and top up my coffee to have a little thing. If you know, then sorry. If you know this already, because you know what a Newtonian telescope is, you could be thinking about how could you improve it even more? What are the things that make an image good? And how can you improve that? Because this design did get improved on. Sweet, sweet coffee. How are you getting on? If you weren't here when I was monstrously faffing around at the start of the lesson, I actually have a Newtonian telescope. I have one. I own one. I'm really glad that I brought it upstairs for you because it's been languishing in my hallway for ages. And now I'm about to show it to you. I'm really excited about it again. I tell you what, you knew this was happening, but I think it'll probably help you to visualise it if I do this. You did know that was happening anyway, but does that help if I show you the rays of light coming off the moon? Okay, so, well, I don't know. I don't want to go too fast on this. Yeah, if you think you've got it, if you've worked it out, could you think about how you could improve it even more? Kind of with the same equipment, but you'd have to put the hole in a different place. You could use the same equipment to actually make a better telescope if you put the hole in a different place. All right, most of you have probably clocked that that curved mirror is going on the end like that. So if that curved mirror is going on the end like that, what do we know about what that mirror is going to do to those light waves that are hitting it? How are those light waves going to behave after they've hit the mirror? They're going to do that. Oh, is it all starting to come together? Light comes from the moon, hits that mirror, bounces off it, all at different angles, so it meets at a point. I have simplified this actually. If you look up Newtonian telescope online, you'll find it's slightly more complicated than this. But basically, that little mirror goes there, and then the light comes out like that, and then your eye goes there. Woohoo! Oh yeah, look at that. Isaac Newton, everybody. Brilliant. So now we can make telescopes absolutely massive because we don't need huge lenses. We don't need lenses at all. So this telescope, I miss you, I haven't seen you for ages. This telescope is not doing any refracting, right? It's not bending the light. What is it doing? It's not refracting. There's no light. Light isn't travelling through a thing and slowing down or speeding up and therefore changing direction. It's reflecting. So this is a type of reflecting telescope. It's the Newtonian telescope. And this is the bit where I just moved on. This is the bit where I moved on in my Facebook lessons. And because I just hadn't bothered to tidy up my hallway enough to be able to bring the telescope. But I have actually got my Newtonian telescope here, so it seems like a good tour. It's really dusty. This lesson on telescopes is also a lesson on rash purchasing decisions and making sure that you look at how big something is when you're ordering it, because I did not look at how big this thing was. Honestly, I had absolutely no idea how big this telescope was going to be. It's really heavy, and I'm not a very strong person, so I don't use it as much as I should do. That's really embarrassing. But I think now I'm showing you, I will. Come on, have a look. So we've got this massive big frame here, and it moves around like this. Oh, I can highly recommend First Light Optics, by the way, if you want to buy a telescope. So if we peep inside, oh, there's a mirror! Look, it's us! And what's this bit here? It's an angled mirror, isn't it? We can't really... Actually, I could show you it because I could put you inside. I can't go inside with my face, but you can go inside. Oh, oops. Facebook's telling... Can you imagine how hilarious it would be if I dropped my phone inside my... Can you see that? I can't see you now. You're in my telescope. Okay, we better come back. I'll have to watch that. I'll have to watch that and catch up. I don't even know if that works. So yeah, we've got that mirror at an angle. Light goes down there, hits that mirror, comes through here, and this is the eyepiece. There you go. Brilliant. So you might be able to see my ceiling. There you go. Yeah, you can. Right. Anyway, that's enough of that. So some people at this point were starting to think about... Oh, there it is. Need my Lego phone holder. Some people were starting to think about which way round the image would be. We get to use our spoon for a final time. How many different activities can you do with a spoon and a glass of water in a lesson? Because we need to talk about another kind of lens, actually. This is in your IGCSE physics and astronomy exams, if you ever wanted to do one of those. Hold the back of the spoon up and look in it. Look in the back of the spoon. You will find that you can see your face, probably, if it's a shiny spoon. And your face is the right way up. So what this is we've talked about a convex lens. You can also get convex mirrors. So this is acting like a convex mirror, right? It's a mirror that bends outwards. If you turn it around, so the front of the spoon is facing you, oh, your image is upside down. So what that kind of mirror is, and you get lenses like it as well, is a concave mirror. I'll draw a picture of a convex lens. This is the classic convex lens. Here we go. I find this one a lot... I'll draw... That's the convex. I find this word a lot easier to remember because it's a concave lens or mirror. And it looks like a little cave, right? If I'm in my IGCSE physics exam and I'm panicking and I can't remember anything, I just imagine like a little bear like living in that little cave. Yeah, there you go. That is what I imagine. So what you're looking at there is a concave mirror. You have to imagine a little bear like living in your spoon. And yeah, again, we don't have time to go into it, but different arrangements of concave and convex lenses do make images be the right way around or upside down. In astronomy, it doesn't really matter most of the time. If you're looking at there's no up and down in space, is there? There's no upside down and right way around. If you're looking at a galaxy in space, it doesn't actually really matter like which angle you're looking at it from. If you lived in Australia, the moon would look upside down, wouldn't it, to us? So it doesn't matter. There's no up or down in space. A lot of telescopes do actually have something on the eyepiece that does flip the image. Because if you're looking at the moon, it's a bit disconcerting, isn't it, if you look at it with your eyes and it looks different to how you look at it through your telescope. But right, we need to look at... I'm not going to make you design the thing that got designed after the Newtonian telescope. The Newtonian telescope isn't perfect. The mirrors can go out of alignment quite easily. If you've got one of those like pirate ship refracting telescopes with just bits of glass in, they're not really going anywhere. So if you want a telescope sort of shove in your backpack and carry around, maybe those ones are better. The reflecting telescopes with the mirrors, you have to sort of, almost like the same way that you keep tuning a guitar, you sort of have to keep tweaking them so that they're all in the right place. The Newtonian telescope is not the telescope that big posh observatories and people who study the sky for a living use, though. Actually, the most popular telescope with observatories is the telescope. It's ever so slightly different. It's called a Cassegrain telescope, and it looks like this, with the light coming out of a hole, which I haven't shown, sort of in the mirror instead. So I'll put that next to a Newtonian telescope for you. This is a really difficult question. Can you see why astronomers prefer the Cassegrain telescope? This is a Newtonian one out here with light bouncing out from the side. This is the Cassegrain one here with light coming out the front. There's something about the Cassegrain telescope which is better, like gives you a better image. We've talked about it a bit. People on Facebook were saying like, oh, is the mirror bigger? I've tried to show you in the diagram that nearly everything about them is the same. So the size of the mirror is the same, like the curvature of the mirror is sort of the same. there's something in this image that you can see that is better about the Cassegrain telescope. Think about what makes a good image. I'm using that word on purpose to be very broad and not give you too many clues. What makes an image good? What do you need a telescope to sort of have? What can you change about a telescope to give you the best image possible? The Cassegrain telescope has got a longer, still written on my board behind me. Not behind me. It's got a longer focal length. Can you see that? On the Newtonian telescope, which I have simplified actually, the focus of the image is more like here towards your eye. But on the Newtonian telescope, it's just kind of boing, boing, boing. On the Cassegrain telescope, it's boing, boing, boing. So the focal length is longer, which gives you a bigger, sort of better, clearer image. So that's why the Cassegrain telescope is generally preferred by astronomers. Let me show you a diagram of what the James Webb telescope does. You might have heard of the James Webb telescope, got launched into space, so it's not been sort of confused by Earth's atmosphere. It can just see into space where there are clouds to slow light down. Amazing! If you like the periodic table, it hasn't got one circular mirror. It's got lots of smaller, incredibly shiny hexagonal mirrors, because that was an easier shape to be able to fold it up and then fold it out when it got into space. And they're made of beryllium because it's very light and it's very strong, but it doesn't actually reflect infrared light that well. So they covered it in gold to make it reflect light better. But here's what's going on inside the James Webb telescope. Look at all that boinging. Boing, 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 boing. So it's got an incredibly long focal length for the size that it is. In fact, the proper word that they use is folded up. It's so clever, isn't it? So the refracting telescopes with the two lenses, like the pirate ones, where the light bent, if you wanted a longer focal length, you had to have a really long telescope. Whereas modern reflecting telescopes, they literally fold up the focal length. It's amazing. So you get a really long focal length in a small space. Oh, honestly, humans, we're so awful sometimes, aren't we? We're so amazing as well. I want to show you quickly a picture of the VLT. Do you know what VLT stands for? VLT stands for Very Large Telescope. Look at that. So the VLT has a, oh, you can see there, look, there's the, that's amazing. I didn't notice that before, actually. That's the angled mirror, isn't it? So the main mirror, the primary mirror of the Very Large Telescope is about 8.2 meters long, like in diameter, which is much, much bigger than this room. I mean, my room's quite small, but still amazing. They're building the ELT, the Extremely Large Telescope, so look out. Oh, just before we go to, I've got a tiny little quiz for you to see how much you've understood. But I had a brilliant question from someone, and it might have occurred to you as well on Facebook yesterday. Doesn't the mirror get in the way of the Cassegrain telescope? I'll show you the image actually, because I thought it was a brilliant question, and it is something that I thought as well, so I looked it up. Here we go. Some of you were like, but you're looking, but there's a mirror there, so how does that work? It doesn't look like a great design. Apparently, I read quite a few discussions about this on the internet. It's because the light's coming from so far away, and the mirror is so very close to where the image is focused. It's a little bit like if you had if you had a marble hanging in front of you 30 centimetres away all the time, it'd be really annoying. But if the marble was like right next to your nose, you might not even be able to see it. It's a bit like that. I think it does affect the image like ever so slightly, but obviously not enough for it to be a problem. The other thing was, if you went to a really big posh observatory, if you decided to be an astronomer, you might be a bit disappointed, or you might be excited, I don't know, to find that really big, amazing professional telescopes are missing something that normal people's telescopes have. The telescope that I have has got a thing that a big professional telescope doesn't have. Which bit is missing if you're a pro? It's the eyepiece. They don't have eyepieces. Apparently no professional studies the stars anymore by looking through an eyepiece and actually seeing what's happening. They're all sitting in offices looking at computers which are pulling all the... So it's just a sensor. I know. Like, it's so much better. We understand so much more about space now because of using computers. There's something romantic, isn't there? I'm sure if you go and visit an observatory, they will actually let you look through. Anyway, that is definitely all the information that I needed to tell you. That was a lot, wasn't it? I'm going to give you 3 questions with some bonus questions if you find the questions too easy. But I'm going to give you 3 questions and they're multiple choice and there's a letter next to the choices. And I want you to just write down, or just remember, because there's only 3 questions, which letter you think goes with the right answer. And then in the end, you should have a mystery word. Are you ready? Here we go. Sorry. Your question, I think this is really hard actually. A lot of people get this wrong on Facebook. What type of telescope is shown in this diagram? And bonus question, if you're like, Lara, I know that. Okay, what exact type of telescope then? What is this type of telescope? Is it S, a reflecting telescope, F, a refracting telescope, or P, neither? So you've got light travelling through a tube, hitting this sort of grey thing at the end, bouncing off the grey thing, hitting this other smaller grey thing that is at an angle, and then coming out through an eyepiece which is at the side of the telescope. Is that a reflecting telescope? If it is, then your first letter is S. Is it a refracting telescope? In which case your letter is an F for fly. Or is it a neither? And your bonus question is, well, can you be a bit more specific then? I will show you the answers again before... I'll show you the question again before I give you the answer. So if you're not sure, maybe you'll guess from what the word is, like what the other letters are. Let's move on. Why are Cassegrain telescopes generally preferred? Is it because they've got a bigger aperture? Write an R. Is it because they've got a longer focal length? Write a K. Or is it because they give a more colourful image? Write an A. And your bonus question is, why is that better though? Like, why is it better to have a bigger aperture? Why is it better to have a longer focal length? Or why is it better to have a more colourful image? Why are Cassegrain telescopes generally preferred? Poor Isaac Newton. Is it because they've got a bigger aperture? Like hole, write an R. Is it because they've got a longer focal length? Write a K. Or is it because they've got they give a more colourful image? Then write an A. I should say, actually, because there might be some pedants watching, or just some people who love facts. The aperture, actually, of a Newtonian telescope is not the hole. It's the mirror, the bit that collects the light. So in my Newtonian telescope, seems weird, but this isn't the aperture. That's the aperture down there. That bit actually collects the light. Moving on. That was just for if people know their stuff and were tutting in the background. What type of lens is shown in the diagram? Is that a convex lens? Write a Y. Is it a concave lens? Write a P. Or is it neither? Write an A. Could have given you a bonus question here easily, couldn't I? I could have said, what is it called where all the lines meet? What is the point where all the lines meet called? That's what I should have said. Ugh, I regret everything. All right, do you reckon you've got 3-letter words? Shall we have a look? Question number 1. What type of telescope is shown in the diagram? Well, what is light doing? Is it refracting? Is it hitting a thing and slowing down? Or is it being reflected? It's travelling down here, it's hitting this grey thing and it's bouncing off. It's being reflected. This is a reflecting telescope. So the first letter was an S. I thought that was quite hard. What type of telescope is it? I think you'll find it's a Newtonian telescope. Yes, Newtonian, because there's a hole in the side and it's reflecting the light. Right. Okay, so we've got an S. Let's have a look. Why are Cassegrain telescopes generally preferred? It's because they've got a longer focal length. So the second letter was K because of all the boinging that the light does before it gets out. That is better because it gives a bigger image. If you remember that diagram that I showed you that went wrong, that I had to improve on. The further away the image is from the lens, the bigger the image is. So that's why it's better. And what type of lens is shown in the diagram? It's not a concave lens, isn't it? You couldn't hide a bear in that lens. It's a convex lens. It's the one that a magnifying glass is. So it's a Y. So the mystery words, trying to catch you out by making it easy, because I usually make it a trick, but it wasn't a trick. The mystery word was sky. So well done if you got that. Well done if you didn't get it, but you're still here. And you don't mind getting things wrong. Right, you lot. That is the end of the lesson. Thank you so much for joining me. Carl, I really enjoyed this one. I mean, I always enjoy them, but I really learned a lot of cool facts that I'm going to remember in this lesson. Whenever I'm live on YouTube, you will have noticed there are no comments running, but I always put up a post on my Facebook page. So at the top of my Facebook page now, if you're watching live, is a post that says, comment here if you're watching live. So if you want to go over to Bit of Science on Facebook and leave a comment, you can, and I will read it out right now. If you don't have a Facebook account, well done you. That's the right answer. Don't feed the evil machine. Just stay here with me. I can see the numbers so that I know that you're watching, and I really appreciate it. I had better tell you, I said at the start of this lesson that I basically busk science lessons into the internet. Everyone's always super grateful that I teach for free. And I'm like, well, I'm honestly, like, I'm only doing it because when I've finished, people put money in the hat. So it is actually a job. It's amazing. It's just something that we invented together in lockdown, really. So there's this website called Coffee where you can support people who do podcasts and things. So I've got a Coffee page. And what I say is, if you are enjoying what I do, if you like the fact that somebody with a first-class drama degree and a first-class science degree and who is a qualified physics teacher with classroom experience is now just streaming everything they do for free into the internet, like everything. No Zoom lessons, no one-to-one tuition. You are literally my students if you're watching this. If you're watching this 6 years after I've recorded it on my website, you're still my student. And you can throw some money in my hat by going to Coffee and signing up. It's put like £5 a month, which sounded like a lot more in 2020 than it is now. It's the same price as 9 chicken nuggets from McDonald's, I found out the other day. So if you want to send me 9 McDonald's chicken nuggets every month, don't do that. But just send me the money and I'll spend it on something else. Have I made this too complicated? Go to my Coffee page. There's a link in the description. Or there's a link on my Facebook page, or there's a link on my website, or search Bit of Science Coffee. Sign up with £5 a month. I'll send you super nice things to say thank you. If you're watching live, I'll send you a past issue of Theatre of Science magazine, which I write. I'll send you some rainbow glasses that make see rainbows. And at the moment, not for long because there's a new thing coming out, but at the moment you'll still get sent another pair of Epic glasses and a little satellite model and some other nice things actually. I could sell it harder. There's other nice stuff around that my husband and I have sort of created and put together for you that gets posted to supporters. But I won't bang on about it. I'll come and read my comments on my Facebook page now. Let's have a look. Oh, hello Aurelia. What's that? It's very colourful. Okay, all comments. Let's have a look. Hi from Aurelia. We had a Christmas telescope last year. We had a Christmas telescope last year. It has no space for a tree, and the tripod made the perfect shape to put the presents under. Aurelia also wants to show you these pipe cleaner flashes she made. Oh, they are gorgeous. Oh, look at me in the background. Oh, like that. You had a Christmas telescope. That's amazing. I can't even do that because my telescope is not on a tripod. Honestly, I thought it was going to be about that big when I ordered it. It was for my 40th birthday as well, so I think we can call it a midlife crisis. Hello, Molly. Hello, Magnus, who doesn't have a Scottish accent, so there's no point in me even trying to do a Scottish accent. Go on. And a picture of a telescope. Thanks, Magnus. Hello, Haydar. Hello. All right, Lewis and Isabel and Thomas watching in Greece. I can't do that accent. I haven't got a clue. Hello, Sophie and Emily and Katie and Hannah. They enjoyed their trip inside your telescope. Oh, yeah, I need to watch that back and see. Was it just blackness? I don't know. Anyway, we'll see. Hello, Abba. All right, you. Hello, Jancy. The cool band that is Jancy. I think that's how it happened, isn't it? I just said Jay and Daisy and Daniel's name wrong once. I just accidentally mashed it together. But now they're a band, so it's cool. I'm pretty sure that I get a percentage when they're famous. Hello, Imogen and Ophelia. Hello, you two. Hello, Hannah and Freya. Hannah says she really liked this lesson. Oh, thank you, Hannah. And we got all the questions right. Oh, that's good. Freya really enjoys learning about the tech side. Oh, interesting. Freya really enjoys learning about the tech side of space travel. Oh, the tech side of space travel. That's interesting. Yeah, I was going to say, I'm really pleased with how these lessons have been set up. So we've done waves and we've done telescopes. Next week, we can finally start to learn about what the actual stuff is in the space, like the galaxies and the black holes and the dark matter and that kind of thing. Yeah, the tech side is interesting. When we did the Lego Story Show about the moon last week, I found myself getting really interested in things like how they took the video of Neil Armstrong stepping onto the moon for the first time. Hello, Bella. How are you, Laura? My show went really well. Oh, good. Good, I am pleased. Excited for the lesson. Well, I'm glad that you were. I hope that Bella now is still excited. All right, Lana and Finley. A few years ago, I got a huge telescope for my birthday, and it was huge. And we saw some of Jupiter's moons with it. And the craters on the moon, and some stars very close up, and it looked awesome. Awesome. Oh, Lana, that's so good. I have a piece of paper full of doodles and facts. Oh, that's nice. Yeah, when I first got my telescope, I got it out like on a whim when everyone else was asleep, and then ran into my bedroom and said a swear. I was so excited. I just woke my husband up, the poor thing. It was like 2 a.m. I was like, Jim, it's like looking on the flipping moon. It's like being on the moon. It's like standing on the moon. You have to come and look at the moon through my telescope. It was like, what? But yeah, it's amazing, isn't it? It's something you never forget. Hello, Toby. All right, you. Hey, there's Lauren. Hello, Science Lines. We went to see a documentary about the James Webb Telescope at the cinema. It was incredible. Really? That is something that I'm jealous of. I would like to see a documentary about the James Webb Telescope at the cinema because it'll all be really big. That's cool. Hello, Ivy and Mum. We have moved house. Now we are getting back into our daily work. Ugh. We're super happy to be back. You've moved house. Oh, that's exciting. I feel like there's 2 different types of person. People who are really excited by moving house and people who are absolutely like fearful of it and really don't like it. Unfortunately, we've got both kinds in my family. I'm the one who loves moving house, like the thought of a whole new place with new things to discover and walls that can be painted. Oh, that's exciting. I hope you're having a good time. No, guys, hold the phone. Robin and Hissy are here. Hello, Robin and Hissy. I love it. And there's a little picture of Hissy looking through a telescope. All right, you. I hope you're okay. And Robin too. I hope you're all right as well. Lovely to see you. Not see you, but you know what I mean. Hello, Jacob. All right. It's Jacob's mum who works in an observatory. So I hope she's not watching because, I don't know, make me feel all self-conscious. All right, Levi and Ezekiel. Hello, Freya and Arlo. We are also coming to your 10:30 class. Hey, awesome. All right, see you then. That's in 26 minutes, isn't it? Looks over at Lego Story. I always do this. I'm like, I better go. And then I just stay chatting for ages. Edmund has sketched the telescope. You did sketch the telescope. Oh, Edmund, did you sketch a Newtonian telescope? This is me finding out if I taught Edmund anything this lesson. Yeah, he did. Did you learn anything this lesson, Edmund? This is his telescope that he sketched. Lens, big lens. Is that the lens as well? And that's the mirror. And that's the extendable bit. Oh, come on. What? Okay. Right. Okay. So actually, this is really interesting, isn't it? I'm looking at this and I'm like, I think I have managed to teach Edmund something. I think so, because Edmund's put a lens there and the lens there. And that bit comes out and that's the mirror and that's the viewing bit. So is this a telescope that would work? Does this telescope make sense? This bit extends and retracts. But actually, like, I want to print this out so that I can draw on it as well. This lens is focusing the light in a certain direction, isn't it? Like this lens here is making the light come together in a certain place. And that lens there is for magnifying the image. So that lens doesn't need to move around, does it? That lens only needs to be in a fixed place so that it can magnify the image where it is. And that mirror isn't doing anything because it's just making the light come off at an angle, but you could look through there. I'm loving this. Oh, this is absolutely making my day because that's all the bits of telescope that Edmund has studied like in their life and knows about. But I want you to draw another telescope. I love that. Thanks, Edmund. That was brilliant. That's really pleased me as that. Because that tells me that you didn't just look it up. There's so much thought in there. That's incredible. Hello, Isabel. Oh, I'm having a proper teacher moment. Like, oh, the brain exercise. Amazing. Hello, Isabel. Hello, Emily and Mam. All right, you. Oh, is this Jacob's mum? It is. It's Jacob's mum. I reckon this is Jacob's mum because they're moaning about having to clean a telescope. Having a big lens means that you've got a big mirror and it's very hard to clean it. Wait, what? Having a big lens means that you've got a big mirror and it's very hard to clean it. The one at Sherwood Observatory is 24 inches. It takes 4 people to move our mirror. Oh yeah, Jacob's mum. Oh right. Shall we look at what type of... I mean, Jacob's mum is literally here, so you could tell me. Sherwood Observatory. I want to know what type of telescope it is. So it is a reflecting telescope, is it? Uses an array of mirrors. I'm just on their website now. The Sherwood Observatory, everyone, you can go there and you can like literally hear Jacob's mum doing a talk about telescopes. It says, this powerful... I'll just show you. This powerful telescope uses an array of mirrors to collect light from celestial objects and focus it for us to view. The current telescope has been built and maintained by the team at Sherwood Observatory. Jacob's mum, did you build it? And is one of the largest public... No! Sherwood Observatory's got one of the largest public access optical telescopes. That's amazing. Oh, there you go. It's a Newtonian configuration. Nice. Not a Cassegrain. 60 centimetre diameter. 60 centimetres, all right. That's quite big, isn't it? It's bigger. Is it bigger than mine? Yeah, it's bigger than mine. Of course it's bigger than mine. Huh. All right. Interesting. Thanks. Reflected along the optical tube into a converging cone of light. Oh, this makes sense to us now. Before reaching an optically flat oval mirror inclined at 45 degrees to the light path. A little bit of feedback for you, Jacob's mum. I feel like we need a diagram here. If I hadn't already learnt about Newtonian telescopes, I'd be like, I don't understand. But I'm really excited that now I can read stuff like light travels along the optical tube into a converging cone before reaching an optically flat image, and I'm like, yeah, I got that. I can totally picture that in my head. Right, anyway, I've finished slagging off Sherwood Observatory Science Communication online. You've got to go. You've got to go and hear it in person. You've got to go and hear Jacob's mum say it, then it's better. Mum was certain the image would be upside down if the telescopes had one lens, and I mentioned maybe it was to make it bigger to see it properly. Now I was right. Bella, how did you get that? I could have stared at that for 100 years now and I've never got that. Hello, Kai. Good to see you. Sherwood Observatory. Oh, okay. Jacob's mum literally just told us. Has a Newtonian reflector telescope. It was built in 1986. So very young. We've got an eyepiece at ours and have to climb a ladder to get to it. Good grief. Ophelia wants to show you her telescope diagram. Excellent. All right, let's have a look at that. I'm loving this. VLT, very large telescope. There is a wonderful... This is Jacob's mum again. There is a wonderful... This is good, isn't it, that we've literally got someone who works in an observatory in the comments. A wonderful 3D model of it in the planetarium software, and I can sit inside one of the telescopes and look up at the night sky as if I was there. You should come and visit us to see all these brilliant things we've got. Yes. Yes, I should. Hello, Emma. Yeah, I should. That's how I... Well, I mean, that's all right. Like, I have put you inside my telescope, like, actually for real. Well, no, not for... Well, kind of for real. I was really worried that I was going to drop my camera phone onto the mirror and that you were going to witness me smashing my very expensive telescope mirror, and then the lesson would also be over. But that didn't happen, so everything's fine. Right, I'm just quickly refreshing my comments to see if there's any more, and then I want to go and look at this telescope diagram. Who will the Silly History Boys be teaching lessons on what day? Oh, well, okay, I'll answer that after I've looked at these other comments. Hello, Lyra, and your cat Nina. Nina's a great name for a cat. All right, Aurelia and Rose, says Jessica. It's very confusing. Hello, Jessica. Here's the bingo bracket from Bluey. Oh, look at that. Wow. That's amazing. Oh, here's Jessica. Oh, right. Been making a Bluey bead bracelet. I'll show a pic. Thank you. For the quiz, I got pride. Oh, good. I mean, like, not good, but I am kind of glad that the mystery word worked out. And then figured out the sky. Well done. On Sunday, we adopted a new guinea pig. Oh, he's 11 months old. Is that old for a guinea pig? That sounds quite old. And a crested breed. He is brown and white, and his name is Logan. I will add a pic too. Please share the pics. I've stopped sharing all the pics, haven't I? Because I feel like it's taking a lot of time, and I really do need to go to Lego Story. But I'm going to look at the pictures of the telescopes. I am looking at... That is gorgeous. That is really cute. And that's really annoyed everyone else, isn't it? They'll have to go to my Facebook page. Oh, he's got to take some antibiotics. Oh. Hello, Effie and Frank. It's Joyful Maths with Ruth, Effie and Frank. This is Frank's fox eating Effie's breakfast. Oh, you've got another origami fox. It's amazing. Hello, Francis. Whoa, you've been given an old Newtonian telescope. That's cool. Which needs a bit of love and care to sort out, but I'm looking forward to using it over the summer. Yeah, that's really exciting. There's Hannah and Freya. Okay, it looks like that's the end of the comments. Sometimes Facebook moves the comments around, doesn't it, and doesn't show all of the new ones, but I'm scrolling through and that seems to be the comments. So let's have a look at this telescope. Oh, come on. This is Ophelia's. All right, telescope tube, nice. Finder scope, nice. Eyepiece on the side. Oh, you guys know too much about telescopes. Telescope ring, okay, interesting. So yours is a Newtonian telescope. I don't think I would have known that before, but now I know if the eyepiece is on the side, that is almost certainly a reflecting telescope. Yeah, all right, cool, thanks. All right, some of you have used telescopes, I can tell. All right, so very quickly, because I really have to go and set up my Lego Story Show, asking about the Silly History Boys. Yeah, it's hard. It's much harder to get them organised than it is to get so there's another Facebook page called Theatre of Knowledge. You named it, thank you. It's like my sort of second business idea where my friends also stream free live lessons in different subjects. So my friend Tempest is streaming Shakespeare lessons from there. And they're going really well. You lot really turn up and watch those lessons. And they've got one at 2:30 today on the YouTube channel, Theatre of Knowledge, so you can watch it. The Silly History Boys are going to teach some history lessons. I keep saying that, like they are, but it's a bit faffy to sort out because obviously like 3 of them are going to teach the lessons. So anything that I say, they all need to discuss it. It's getting complicated because they've already got a coffee page. And I'm going to take 20% of what the teachers earn for all of the admin. It is a lot of admin. But I've said 20% now, so it's too late. But they've already got a coffee page, and it's like, do we set up a new coffee page? Anyway, sorry, you were just asking about the timings. If they manage to sort of sort it out so that it can happen, it will be Fridays, I'm pretty sure. Rob sent me a lesson to look at a couple of days ago, and I really liked it, and I need to send him feedback about like tweaks that he can make, because it's quite a specific thing to do. It's not like classroom teaching, and it's not like teaching like acting in real life. It's a real particular set of skills or like things that you need to know to teach to teach you lot, basically. So it was really interesting. It was really interesting because Rob's lesson was brilliant, but he was treating you like you were students, like in a classroom. And I'm going to have to say to him, like, it's not like that because they're choosing to be here. So there's certain things you have to do in a classroom that I don't have to do because I know that you want to be here, like you want to learn. Anyway, I'm just waffling on now and I need to go and tell Rob that stuff. But yeah, I think almost certainly Fridays. I think I'll probably say to him now, let's start after half term because like the coffee pages and the YouTube channels and stuff need to be set up. So yeah, sorry, that was a really long way of saying probably Fridays, probably after half term, but we're still bashing it through. When I know and Rob knows, then you will know. But it is happening. It's all happening in the background. Okay, I'm going to go because I've got 15 minutes to set up the Lego Story Show, which is about lizards and chameleons and geckos. So go away and have a screen break. I'll go away and play with Lego, and then I'll see you in 15 minutes on this YouTube channel for learning about lizards. Okay, thank you so much for supporting me. Thank you so much for paying my wages so that I can do this job. If you don't put money in my hat, I can't do this job. I have to go and like work in a classroom. It should be fine, but nothing like as good as this. All right, I'll see you a lot very soon. Thank you. Like and subscribe. Bye.